welcome back. Sorry, I'm just trying to figure out this camera. Let's do... Here we go. Yep, okay. I think we're doing okay. We are. It's a miracle how this thing's working. Okay, so this will be 3.1, Measures of Central Tendency. So for the last two sections, we've kind of been focusing on more of the preliminary stuff. So, like I said before, we just completed 2.1, and that's organizing qualitative data, which we have not gotten to yet. But now we're going to get into the bulk of all of this, the actual dinner that we're supposed to be eating. Chapter 3 and Chapter 4 are actually a little bit distinct from each other. You know, you can do one without the other. Same with 2 and 1. You don't, that's why I'm kind of hopping around. I don't have to. So, what I'm going to do is, I'm going to go straight over to 3.1, Measures of Central Tendency. So, this is a very easy section. You cover it in every Algebra 1 class. We're going to fly through this. So, I'm just going to have everyone be prepared. This is going to be one that we kind of go through a bit quickly. I'm just going to mess with the camera. Here, we tilt it. There we go. Okay. So, this chapter is a denser chapter than many of our others. You'll see with like chapter 1 and 2 preliminary. Chapter 3 and 4 are actually preliminary as well, but they're dense chapters. So we're going to have to get through them over time. That's why tomorrow I decided to do 3.2 tomorrow, because 3.2 is pretty dense. So we haven't done 1.1 yet. That is tomorrow's game. We will be doing 1. What is that? So this is 3.2. It measures of variation and dispersion. If you can see, it's quite a few pages, but it's so dense, and I need to explain quite a lot to get through that. This one, section, chapter 3.3 is a little bit dense too. Not horrible, but still. And then I've got 3.4, which is a bit dense as well. Actually, 3.4 is the biggest, 3.4 and 3.5. So, we're gonna just get started with 3.1. Okay, here we go. And we will be using our calculators today. At least I will be showing you. I can kind of get it a little bit close. If I move the light, we can probably see it. Yeah, maybe. But then you got the glare, so, let's not worry about it. So, here we go. So, what is a central tendency, and what are the measures of central tendency? Because that's the first thing I was asking myself when I began this. So, when I think about central tendency, I think about when I have a group of numbers, what is the tendency for it to be central? Or what is the tendency for all of the numbers to have a center? Or, well, let's more of the focal point of the center. So in a group of numbers, you kind of have, like, where is it centered on? Now, the thing about it is that this definition of central tendency is very vague, which is why we come up with 3 interpretations. I'm going to call these interpretations of central tendency, because that's kind of what they are. They're true as much as we like it, because they're so right about it. Here, I'm going to try this. Okay, it's not going to move, but you can see everything. So, the first interpretation is mean. The second interpretation is median, if I can find it, right here. And the third one is mode. So that's what that is. So each one interprets the idea of a central tendency distinctly from the others. So it kind of makes it interesting how we go about it. And so we will get 3 separate numbers. So the first interpretation of central tendency, and when I say interpretation, I'm not trying to say, it's not right or it's just an interpretation. I'm saying that it's a different perspective of looking at a central tendency. I'm gonna move this light because it seems like it's glaring a little bit. Yeah. Okay, actually, that's kind of what we gotta do. Oh. Like I was saying before we crashed and burned, actually, this moved great. Okay, there we go. I got more problems with all this stuff than most people. It's working though, so we're just gonna go with it. Okay, so it's kind of tilted a little bit, but you know what? Oh, that's just annoying. You're supposed to do this all before, but I'm just, there we go, that's a better, like that. Well, we're back to that. Okay, whatever. Okay, so what we have here is the mean is an interpretation. It's looking at it from a different perspective. So let's say it's a different perspective of when we look at a center. That's pretty much how it is. So the arithmetic mean is the measurement of most people think of what they think of average, But the problem that I have with this definition of average is what is average? And I can't really explain what mean is. I'm going to be honest. I don't have a conceptual understanding of it. I can't comprehend why we do mean. I can do all these lovely numbers and all this stuff and find it, but I don't even understand. So that kind of inhibits me a little bit. So, with the arithmetic mean, it is computed by adding all the values, so it's summing up in the variable of the data set and dividing by the number of observations. So here is we have two arithmetic means, and we haven't gone into population and sample yet because we skipped that in 1.1, so we will go back to it. But the main point is a population mean, or population is the full group, while a sample mean is a sample of the group. And this means different things in different situations. But right now, both of these are pretty much the same equation. So what you do is you take the sum of x1, and xi is like, the abbreviation for pretty much the summation of all of what x is. So if you look down here at this table, let's say x was the number of pets, and we wanted to find the average number of pets. So what we would do is we would find the summation of x1, which is going to be all these numbers, and then we're going to divide it by the initial number. Now we'll get into more of this later and what n is. So with a population, it's a parameter. Parameter is like a measurement of a population, while a statistic is a measure of a sample. We'll get more into that in section 1.1 tomorrow, so do not be frightened. So in a population mean, again, it uses data for the whole group, and it does not vary. It is always, always, always constant because it's always with one group. But with a statistic, it uses data from a sample, and it varies because you can have different samples. And the one thing that I want to note here about the difference between sample and population when it look at studies. So if I did a study of 100 people, and another person did a study of another 100 people, the same group of people, but we got different results, that can mean that if we're trying to find a causation, like we stated in 1.2, okay, let's try this again. I do apologize. So, we're going to bring this down a little bit closer. There you go. So now you're just a little bit closer to me. You're on the ground now, so actually there's a little bit more. Oh, here we go. Okay, so this is just going to shine right down here. We can go for a little bit of a high. I do apologize. This setup is not perfect, so this does happen, and it should have been edited out, but it wasn't. So that was just waiting to happen. Dark. This. Let's go down here. Okay, there we go. I guess that's a good. The thing about why the the phone's being charged. It's pretty good phone, the Google Pixel 2. I like it. It's pretty nice. Um, and it's connected to the lamp, which has an outlet on it. That's why I'm using both of them, because it's way more convenient. But, you know, this thing's on a yeah. It's a weird setup, but it works. So the one thing that I'm talking about is studies. So in a study, if you're trying to find a relationship between things like the causation that we were talking about in 1.2, then what you're going to end up having is, let's say you have three different samples of the same group of people and you're getting different results, you might be looking at the wrong causation. So that's the thing about samples. But with a population, it's always constant. It never changes per sample. But the sample mean will consistently change with each sample. So that's kind of the difference. Example 1. Suppose you are interested in the average body temperature. Explain the difference between this Greek symbol and the X bar symbol. So remember, it's the same thing as that if I'm interested in the average human body temperature, the U symbol is the entire population of humans. And that's actually improbable. It's very impossible to do that because you would have to get all of every human being, and you can't even find every human being. You know, I can barely find my neighbors down the road, but you know, it's the same thing. Yeah. So remember, the U is for everyone, the X bar, and if you statistics and chemistry are kind of aligned, you'll find this X bar in many different places sometimes. So there's just a little bit of an interrelated when it comes to the mathematics. So the X bar is the mean of a subset or sample. So if I'm trying to find the sample of the average human body temperature for everyone that lives in a cave dwelling, then that I can kind of try to do that with a little bit of a sample, but there's not many people. So we have some notes down here. So these will not be the same, and they should be close to the same. And that's because of the distinction between a sample, or a statistic, and a parameter. Very big distinction in all studies is pretty much from this. And so that's kind of a problem. The difference between you is very important. Very important for almost just anything. Study, everything. And the one problem that we have, which is a big fallacy, is when you try to take a sample and extend it to the population when you have such a small sample. Sweeping generalization. But it's a little bit different than actually trying to infer from a population because, that's just how it is. Find out how many pets each person in your class has. So this was all recorded from online, and we just found the mean. And what we did was we took all the numbers and we added them together. So all of the numbers of pets was added together. I don't remember. And then we divided by 32. So we took the summation of xi, or x to subscript I, and we divided by n, which was just 32. So it ended up being the summation over 32. And that's how we did that. So this kind of example isn't too bad. We can go find it really quickly. So this right here is how we find it on our calculators. Now this is kind of easy. So if you have a TI-84, which is required for this course, all you have to do is go to the list, which is stat, enter, edit, then you got your numbers, and then you go up here and you clear, and you put new numbers in. You put new numbers in, so like back here we put new numbers in, and then let's say here we'll do, let's say we do 1, 2, 3, 4, 5, and then over here we're gonna have, well no, we'll just do this. So then what you're going to do is, in order to find the statistics, remember stat is just an abbreviation for statistics. You'll always see it on the caption of this video or every notes video. So you're going to go to calculate. So edit is when you're going to edit the list. So 1, you actually go into edit. 2, you actually sort. 2 and 3, you sort. 4 is clearing the list altogether. And 5 is setting up the editor. But you know. So calculating, you're going to go to calculate, and then you're going to do one variable. And we're going to do list 1, and we're going to find out our mean, median, mode, and everything in between. So, if you take a little bit of a look closer, we actually found our mean. I'll bring it into the light a little bit, there's a glare. So it's x bar equals 3. So for this sample of 1, 2, 3, 4, 5, we found it. And this is all this is staying right here. This is just how you find it, calculate, and then you just go down to first variable statistics. So, and then there's some more information, but if you have a TI-84 calculator like this one by Texas Instruments, which I think I can put a link down below in the upcoming videos for this calculator, then that's just what you do. More important information about the mean. So the mean is frequently not a value from the data set itself, and that's something too important when you're looking at an interpretation of this central tendency, is that as a central tendency, it doesn't come from the data set. Compared to median and mode, where you do have it, it's a little bit different. Then, the mean is the balance point, so that's a good kind of understanding. That is, if you imagine a dot plot of the data, then the mean is where the data set perfectly balances like a fulcrum of a seesaw. That's very much more important to look at it from the mean. So if we look here, the kind of middle point is going to be, yeah, kind of like right here. Right here, you're going to have the teeter-totter. On this side, it's all going to be even to this side. And this is the focal point. So that's kind of how that is. Okay, the following dot plot shows the numbers of representatives by state. Find and label the mean on the graph. There are 435 representatives. Remember, the representatives change. I mean, it's irrelevant from the graph, but every 10 years it generally does change. There's 435 representatives in 50 states. Okay, the means. So what does it say? Find and label the mean. The mean's right there. So all you would do is see this, the number of representatives per state. Well, this is a little bit distinct. So it was already done before. Remember, I'm not on here to crunch numbers. I'm on here more to kind of go over conceptual ideas. So crunching numbers is I kind of already showed you how to do it. So it's kind of just all about getting that through. The means for the graph below are 4.94 and 2.88. Explain which is which. Actually, we got it from 435 divided by 15. So yeah, but that's, we don't need to do that. And that's 8.7. Because you've got a lot of states over here that are like, especially the New England states, kind of smaller. You don't, especially out in the West, you don't have smaller states because of that kind of principle of manifest destiny kind of made them bigger. But, you know. So the graph here, so we're going to look. So if these are going to be considered like a fulcrum of a seesaw, then when we have a seesaw, okay, and let's say we do have a seesaw, so where is kind of the even point here? Where is it even half and half? And so we wouldn't want to put it right here. So with 4.94, that kind of doesn't look correct. And so this one's going to be the 2.88 because, you know, there's half on this side and half on this side. And, you know, they're about the same even, but remember, like, 1 is much bigger than 4 or 5 or 6 or 7 or 8. And even 0 is higher than 7, 8, and 6. Then 4.94. Yes, so 4.94 will be lopsided. Sorry about that. I'm having such a hard time with this today. I do apologize. So the graph B, 4.94. So if we had 2.88, it would be right here. this is not half and half. This is actually more like one side's on the ground and the other side's up. So there would be no balance. But 2.8 would be much more lopsided. And 4.94 kind of seems about right here. So, I would almost say it's a little bit more than that, but it's just the representation. So you've got half on this side and half on this side. And that's how you look at that. Okay, mean. I know we're already at 20, but, Okay, so the next two we're actually going to get through pretty quickly because they're not as big. So median is what is known as separating the lower half of the data set from the upper half. This is always going to be one of the numbers. And median's looking, so when we think of mode, it's pretty much a halfway point. It's half is on this side and half is on the other. But with the median, it's actually the numerical value. It's not the actual arithmetic value, it's the numerical. So it separates the lower half. Remember, it's not like a fulcrum. Yes, it's not like a fulcrum. It's not going to be, it separates it as a numerical value. So the data should be arranged in ascending order if you're going to find it by hand. Remember, you always, especially when you always find it, it's just that. The calculator finds the median. It finds it right here. Median is going to be, what is median? Median is resistant. Median is M. Median's right here. So median is 3 on this one. Median is resistant. So a big thing about this idea of resistance is that when you have outliers on a data set, okay, especially with central tendency, it moves that central tendency quite a bit. So what we're looking at here is so with mean, if mean is the fulcrum point and we have an outlier on here, then, it's going to tip a little bit left or right. And that's because it's kind of like a fulcrum. If you put just a little bit more on one side, the mean moves a little bit. But with the median, if you add another one, it's gonna kind of move maybe one, maybe none, maybe just a little bit, maybe half. So it moves less, so it's resistant to those extremely large or small values that are in the data. But with mean, if mean is always looking at it from a fulcrum, you put a little on one side and it tips over. And mean always wants to stay absolutely balanced, but median doesn't really care. And this is not median, this is median. Find the median for the table set for example 2, the pet data for the class. We found it was 2. So we go back to here, and then we did it in ascending order, and that's just kind of number crunching at this point. So it is 2. Example 6. Suppose a new student walks into our class at this point and they own a petting zoo with 127 pets. Find the mean, which is a lot. Find the mean and median for our class pets data with the set added into our data. So remember, the median is still 2, okay? And you know why? So when we looked at it from ascending order, we looked at it and we ascended it. And there's multiple 2s throughout this data set. So when we looked at it and we said, well, it's only going to change by 2, or it was 2 plus 2, it's only going to move to the right 2. Or, well, it's only going to move to the right, and it was already 2. So it doesn't matter. But the mean has moved entirely. The mean here is 6.0909. And that's because when you're looking at mean from a fulcrum point, it's tilted a lot the other way, because it's not resistant. Think of median as a boulder that only moves every now and then, and think of mean as the kind of fulcrum. Why do you notice about how the student affected the mean and median? See, this is the same thing. An extreme value has a huge effect on a mean, but not on median. Mean changes because it is related to the values of all numbers, whereas mean is related to the amount of numbers. And that's a big distinction. That's how the perspectives change. One looks at the actual value of all the members, while the median is related to the amount. And so it's kind of hard to wrap your head around a little bit, but that's the distinction, is that point. And that's why they're separate. The arithmetic mean is sensitive to extreme or very large or very small values in a data set, while the median is resistant to those values. Which measure of center is a better representation? So the one thing that we want to look at is because mean moves, because as a perspective it looks at it differently, one perspective is generally better than the other. And so here, median is, because it was related to the numerical value, that represents the upper half and the lower half. So it's always going to, so even if you add a little to the upper half, it might not even move, because it's only related. Now if you add a lot on both sides, it might not move at all. But it depends on the frequency. Very hard to move, but at the same time, you can still move it. So there's another important note. When data are skewed, the median is the preferred measure because it doesn't tilt like a fulcrum. It's kind of like a boulder. So then we have this right here, which by design seems a little precarious. So with this goes on the exam sheet. I get a new sheet of the exam. So this, you might not be able to see it. Let me bring it a little bit closer. So here you can kind of see where we have it where it's skewed left. Here, let me take a look at the camera. You can kind of see it if we got in a little bit closer. Right there. So what it's showing is that if the mean is less than the median, then it's going to be skewed left. And this is how the relationship works. You kind of have this representation where, median or mean, if mean is less than median, then the better measurement is median. Because remember, you have the fulcrum. The fulcrum has fallen to the right, but it says it's skewed left. That's because there's an outlier out here. That's what that means. So there's an outlier out here, and for this one there's an outlier out here. But think of this, so draw like an arrow down the middle of each one of these, and then show me. So we would think that, the mean would want to move this way, because there's so much data on this side, while right here, the mean doesn't want to move at all. And then even compared to this one, you have an outlier out here, so then the mean tilts the other way. Or, well, the mean tilts more this way, actually. So the mean tilts towards the outlier. That's what I mean. But the median does not. The median is more resistant. So it's skewed left or negatively skewed. It's skewed right because you have an outlier on the right or an outlier on the left. Now, this better measure of spread, we will get into these later. Very important. That is actually the next section. So that's just how it is. Bring it a little closer. And so there's a warning down here that says these guidelines for skewness as it relates to mean and median work well for continuous data but not for discrete. Don't worry about spread until 3.4. So that's going to look at, we haven't got to 1.1, so you won't understand continuous or discrete data set yet. Or if you do, then you know what it means. But, the mean is about, it's not exactly there yet when it comes to this. So when it comes to a symmetric system, it's similar, but it's not necessarily absolutely symmetrical. But if it's like you have an outlier, then it's not. So example 7, I did do example 7. I don't know why it's not on here. But what we're just going to do is we're just going to show right here, you kind of have the mean and the median are similar. So this is going to be A right here. right here, the mean is greater than the median. So it's going to be skewed to the right. So there's going to be an outlier. That's right here. And then this is, of course, going to be this one. But the mean is less than the median. And so this is going to be A, B, C. Okay. Let me zoom in a little bit. There we go. Okay. So this is mode. Okay, so we're almost done. We've got like another 4 minutes. So, mode is the most frequent observation of the variables. Remember, so median is like, what separates the upper half and the lower half. The mean is the fulcrum point. But the median is an entirely different perspective, and one that's very easy to understand, but also kind of a pain. So the most frequent observation of the variable that occurs in the dataset is the mode. The modal class is the group or category that occurs most frequently. So let's look at example 8. A. Find the mode of the pet data from example 2. So back here from example 2, we're going to look at the pet data. So it pretty much looks like there's 4, 5, 6, 7, 8, 9, 10. Compared to 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3. That's about it. For 5s, there's only 1. 9, there's only 1. 8, there's only 1. 4, there's 1, 2. So it is 10. Or it is 1, sorry. But there's 10 of 1. Oops, my face. So, the mode is 1. Find the mode for the birth month, or find the mode birth month for the 2012 Detroit Red Wings players. So along this graph right here, we see that February is our top mode. Find the mode of the data set right here. So the thing about this data set is there is no mode. And the one thing that the instructor put here was that this was mostly a continuous set, that when it continues on, like height or whatnot, there's generally not going to be a data set there. So that's something to throw out there. Then we have find the mode of the data set. So you got 1, 1, 2, and you got 3, 3, 4, 5, 6. And 1 and 3 are the actual data sets. So then right here, we're going to look at the disadvantages and the advantages of mode. So as a perspective, it's very distinct from median and mode, or median, mean, and median, because both of them have a special relationship with each other, but mode really doesn't, because mode can move around, whatever has the most frequency. And so as a measure of central tendency, or as a perspective of central tendency, it's very important because it's showing you a different perspective altogether. So the disadvantages is that there are some that have none, mostly with continuous datasets, like number C, or letter C. Some datasets have 2, 3, or 4 modes, and that can create a problem because then it becomes a bimodal, or trimodal, or a multimodal graph, which looks very weird. And then TI-84 calculators cannot find mode at all. So that kind of inhibits a little bit of things. You kind of have to find it yourself, but it's pretty easy. So the advantages of mode, it is the only measure of central tendency a variable for the qualitative nominal dot, or data. Sometimes it's for ordinal. So it can be used for ordinal sometimes, but we haven't gotten there yet, so we're going to kind of leave that note kind of unchecked. And then the mode is often easy to calculate. So easy to find. You just have to know that it's the most frequency. And so that's mode. That's all 3 of them. Pretty easy to find, so, we're going to kind of leave that up in the air. And I will see you guys all back here